Hello, here's episode 34 of the Phase Space Invaders podcast, where we explore the landscape of computational biophysics, and my guest today is Rafael Bernardi. Rafael is a professor at the Department of Physics at Auburn University, and his group is part of the famous NIH Center for Macromolecular Modeling and Bioinformatics. That also includes two former guests of the podcast, Alexei Aksmentiev and Zanluthe Schulten. Within the group, Rafael carries a large part of the responsibility for directing the development of the tools we all love, the molecular visualizer VMD and the molecular dynamics engine NumD. But aside from that, of course, he runs his own independent research agenda that revolves around questions of mechanostability of biomolecules, force transmission and resistance, allostery and adhesion. So we start from discussing the applied research angle, talking about the molecular mechanisms of catch bonds, all the theoretical peculiarities of studying force-induced phenomena on the atomistic scale, and modeling results from atomic force microscopy, AFM for short. That serves as a segue into the question of software development and how important it is for our tools to answer a need that actually exists out there, especially when we do that at scale, as happens with both VMD and NumD. We comment on the ongoing release of VMD 2.0, which I encourage everyone to check out, and the shift in philosophy that motivated this development. We end up defining, half jokingly of course, a mini manifesto of contact-based biochemistry, a perspective on biomolecular events we both share from the points of view of our respective research programs. Plenty of cool stuff, so as always, enjoy our conversation. Okay, so Rafael Bernardi, welcome to the podcast.
Well, thank you. Thank you for having me here.
So Rafael, your research in the last decade or so has been deeply embedded in the NumD VMD community, including major contributions and supervision to the software ecosystem. But I have to say I'm also quite passionate about your other research lines, such as nanomechanics, allostery, mechanostability, force transmission. I even have a hint that some of those fundamental scientific questions might go back to deep history when your postdoc supervisor supervised the postdoc supervisor of my PhD supervisor, as they both, Klaus Schulten and Helmut Gruppmüller laid kind of the foundation for the study of molecular mechanics in the most literal sense of the phrase. Do you mind sharing what brought you into this specific field? And, it always feels like destroying molecules should be straightforward, right? But I assume we have actually learned something about that since.
Yeah. So, okay, I got into this kind of by accident. I came to work in Klaus' lab in the US. I'm originally from Brazil. I came from Brazil to work in Klaus' lab to study biofuels and second generation biofuels. So we were interested in studying enzymes that degrade biomass, blood biomass. And one of probably the most efficient enzyme that does that is a large protein complex called cellulosomes. And the cellulosomes have some interesting mechanical properties. So coming to work on biofuels, on enzymes that degrade biomass, and then cellulosomes actually got me in contact with Klaus's friend, Hermann Gaub. And Hermann was interested in the cellulosomes as well because they form these large complexes that should be mechanostable. So Hermann had a group leader at the time, Michael Nash, who was interested in pulling on these complexes, and we start pulling on them together, kind of like trying to understand how we engineer these large complexes. And that actually got me into this mechanobiology because we started to study this is quite interesting, like the mechanics of these systems. And we ended up collaborating like Klaus, Hermann, and also Ed Bayer, who was the one who discovered the cellulosome. So we had all these big names, interested in studying that. It was very nice. It was a very nice group. And we actually started to learn mechanics that people could not learn before. And that got me kind of hooked into this world of mechanics.
Right. So I assume this is something that's just a structural element, right? That kind of conveys rigidity. Or why is it?
Yeah, so the first system that we studied was a cellulosome. And I think what called my attention, I think that made me so passionate about it is because it was definitely not obvious. So the first part is this is a catch bond system, and a catch bond is a bond that, like, explain this shortly, like regularly a chemical bond is what we call a slip bond. So that means that if you apply a higher force, they leave less. So like if you apply a little force, they might leave 5 minutes. If you apply a higher force, they'll probably leave 1 minute. Now, catch bonds are the opposite. If you apply a force to them, they leave longer. So they can get hooked. And the cytosomes end up being these like cohesion doctrines in cytosomes end up being catch bonds. And when we were simulating them, it was the first time that somebody could show really like clearly, atomistically, the mechanism of a catch bond. A catch bond, not because like we have seen since then that catch bonds can be actually very different than that. But the first one was very interesting because we were pulling this system that has like very flat surfaces, like basically there's a flat surface from the cohesion, a flat surface from the dockery, and you pull them apart, the contact area goes up.
Oh yeah.
It's completely not intuitive, like you're actually pulling something apart and imagine that they are actually getting tighter. And this is pretty much like one of those Chinese finger traps, like that's typically what I use to demonstrate this. Because the finger trap, basically, like if you go very slowly, you can remove your finger very easily. But if you pull fast, you lock and it basically traps your finger, right? The finger trap. So these molecules are doing similar things. They're getting trapped in those conformations. And that is like so unexpected to me because I think like we can think about large things and engineer a system that is like that. But like doing something at the molecular level that is doing the same thing was like, whoa, like that's like had this wall kind of thing on me. And that's how I end up getting another one. I'm like studying another system. And now basically what we do is studying those types of systems.
Yeah, it kind of defies our intuitions, right? Because we maybe as simulation people or mechanical statisticians are used to thinking of equilibrium properties that are path independent, right? But you have a clear path dependence here, and like you have to go to all those kind of non-equilibrium methods.
In terms of simulations, it's kind of like we are typically doing like SMD and those like steer pullings and things like that for calculating free energy. So we want to go like at the quasi-equilibrium regime. Like in my case, it's opposite. Like I want to study the mechanical property. I want to see what is happening when you give like a big pull on those systems, and it's very different, and it's actually extremely biologically relevant. It's just that we don't study it so much because the tools were not there, both computationally and experimentally,
Well, you would think that a lot of nature has mechanical properties. Like nature is pretty mechanical, but I would say there's probably very few specialized molecular components that actually carry most of the loads or do most of the adhesion or force resistance, right? So like in the whole biological landscape or universe, it's a pretty specialized corner.
There's much more than we usually think, like
Oh, really?
Yeah, so there are, like, we have been seeing more and more over the years. And some of the reasons are, some of the systems are super mechanical resilient, meaning like the tools that we developed, like you have to remember that pulling proteins experimentally was developed in the 1990s. So like these are like the first proteins being pulled. So
we're talking AFM setups, right?
AFM like by Hermann Gab, like slab, so like this is kind of like some of the first experiments, and people doing also with optical tweezers, trapping molecules, late 80s, early 90s, like pooling, doing like single molecule force spectroscopies is relatively recent. To do that really well, to do that kind of a standard technique is something from the last 10 years. Now, going into high-level forces, it's actually one of our papers was the first one in 2018. Like to go like beyond like strep avidin biotin, like going kind of beyond the normal strong, because the whole like you have to engineer the whole surface chemistry to be able to do it, and like how the experiments actually get more and more complicated. Also, there's the other side of it. A lot of these forces happen inside cells, and you want to study them inside the cells. So there's a lot of people developing tools to study at this like cellular scale, like very small forces. And so there's a lot of molecules that we just don't know yet. And there you see them popping like in new conferences and new editions for like large journals, like on mechanobiology, a lot of molecular mechanobiology. There's a lot of coming up these days.
I see. Is it more like inside the cell or between cells in the sense of adhesion versus transport, or
So
both?
my group studies more the highly mechanostable, so they're usually outside the cell.
Yeah.
But a lot of the mechanobiology being studied at the moment is inside the cell. So these are like a few piconewtons of force, sub piconewtons of force, and make the whatever action you need.
Well, we do study the ATP synthase, which is like another project that was, shared interest between Helmut and Klaus, if I remember correctly.
Exactly.
So
Yeah.
I'm kind of familiar, but then of course it's like a molecular machine that has a time scale well beyond our simulations, right? So like the question is always to what extent we are capturing the relevant time scales with the latest simulations. Is it already there to kind of see the biological scale or experimental scale, which can be also different, right?
So if you look at the ATP synthase, you are looking at like this rotational motion that happens in a much longer time scale than we can usually simulate. You can use, of course, some enhanced sampling methods and all of that. The point that I was trying to make is like an ATP synthase is going to produce maybe a couple of piconewtons of force stroke to make that rotation. While if you go outside of the cell and you're looking about adhesion mechanisms, you are on the hundreds of piconewtons to maybe a couple of nanonewtons. So it's like 3 orders of magnitude sometimes stronger. Remember that to be that strong, you also means that the lifetime of that bond goes to infinity compared to our time on simulation. However, if you want to study their properties when you're breaking them, simulations are pretty doable because you want to keep pulling until they rupture. So you can actually make that much faster. Of course, the experiments are not that fast, but there are theories that can connect the two speeds and you can study.
I remember a paper that essentially looked at Shatavidin biotin and I think connected the 2 time scales, right? That was a couple of years ago.
There's a paper by Helmut Miller, like the simulation part, and the experiments were done by Felix Rico. Yeah, they published a few years ago. It was a PNAS where they connect the two worlds. We actually have something on the pipeline very similar to that, where we are pulling in many, many different, like we have 10 orders of magnitude different speeds on AFM and the simulations.
Yeah, because that's also becoming another validation of whatever force fields in our systems, right? And there's so many variables that you can get right or wrong. I know that you also looked at directional pulling, right? So like you can have different directions in which things are being stretched.
Yeah. So one of the consequences of the things that we have been studying is, we started that because we wanted to understand discrepancies in the data. And the discrepancies here were, if you look different labs, they were getting very different results for the same pooling. And sometimes even your own data from the same lab was getting very different results. And that was for strep-avidin biotin. And one of the things that we noticed is that, that's kind of like, it's discussed in the literature, but not well, kind of like people kind of know, but could not prove, was that this was related to tethering, like meaning like you're using reactive like amines to do it, like anything that is kind of any amine that is exposed, and then you hook there, you're a strep-avidin. The biotin is pretty well controlled where you're pulling, but the biotin binds to the strep-avidin and you pull. But now your pulling geometry differs depending on where you were hooked. So what we were able to do is both experimentally and computationally pull from different places, kind of create a way of knowing where you're pulling in the experiment. And then, of course, the simulation is very easy. You just pull wherever you want. And then show that the different results were actually coming from pulling from different places. And when you, of course, have like dozens of different places, this becomes a huge distribution. You don't notice that there's actually many different places, but you can actually get these different geometries causing a different result. Again, there is some counterintuitive results out of this, which is very interesting in my opinion. Is strep-avidin basically locks biotin, kind of like your hand going around another finger. And one of the geometries is the geometry that kind of forces this out and opens your hand, kind of force the biotin opening your hand, opening strep-avidin, right? And you would at least myself, I would initially assume that, okay, this is the strongest one, because the other one would be kind of like taking your finger straight out, like without destroying your hand, without destroying the strep-avidin. But actually, filling is cheaper than breaking many bonds at once. So
Yeah.
the one that you go to the side and peel the strap-avitine off, basically break the whole strap-avitine, is weaker than the one that if you pull just straight out. And I think those kind of, when you think about it, yeah, it makes sense because you're breaking like 10 bonds at once instead of breaking one at a time. But it's
Right. Here's where the path dependence comes in.
yeah.
And the way, of course, you're showing things with your fingers, which is not going to be captured by a podcast.
I know.
But I remembered immediately this idea of the haptic device for VMD, right? So is something like that actually being useful when looking at responses and getting intuitions about forces? I mean, I'm referring to this because, you're also a big part of development of VMD and the many tools that are being added on top of that.
No, this is, a lot of the times, this kind of tools like the haptic and a lot of these gimmicks are pretty fun, but I would say they are not so useful on a daily basis. It's not a major effort on development, I would say. You're not doing anything on that direction at the moment.
Right. But how much of a help is it that, you're doing your essentially research agenda together with software development, right? Because you can kind of steer many directions in which both VMD and NumD are going. And is that helping?
It does, of course, because when I was in Klaus Lab, because of the funding mechanism we had at the time, the way the biology was treated was what we call this driving biomedical problems. So we had driving biomedical problems that would push the boundaries of what the computational needed. And then we would develop softwares to kind of accomplish that. The idea basically remains in my lab. I like that idea. I like the idea that we are pushing the software development because we need it. So in that regard, there are a lot of tools that come out in VMD, sometimes because we need them. There's the VMD tree has a huge suite of understanding contacts and hydrogen bonds and how you analyze them, how you make contact, networks of contacts. All of that is something that we have been doing in our lab for a long time. We just put it into a nice tool inside VMD to speed up things in our lab, especially training new people, because the old people like myself are not learning any of those tools anymore. You're basically writing scripts to do it. But the younger people that get into the lab, it's a much faster path to learn how to do it. It honestly is a much easier tool. I think it's what we do then is to create these tools that help people to do the analysis that we are doing. So inside VMD, I would say these contacts and networks and all of that is getting more and more space because we use them a lot. Same way for free energy methods and all of that are becoming more part of VMD and at least on the VMD side. On the NAMD side, I can tell you that there are some pushes too. Like SMD was one of the first tools to become multi-GPU resident, in NAMD. We used it so much that we wanted that. There are other developments in NAMD that are kind of pushing the same direction. Like we recently needed more ways of keeping very, very long simulations. We had to make a few changes inside NAMD so that we will not break anything because we're going to many, many, many microseconds of simulations pooling. And so that was breaking some stuff. When you create these tools, sometimes you don't imagine that people are going to pool for 10 trillion steps,
Yeah. This is the common thing that in Amber, for example, you set the number of steps and it's stored in a standard integer, which can only be 1 microsecond.
Exactly.
And it always breaks something on a technical level, yes.
Yeah, but usually you solve those problems with workarounds very easily. But when you're pulling on the system the way it's set up, you actually cannot. So we had to fix some of that.
I think it's a common feeling that a lot of time gets wasted on solving the most trivial questions, like formatting of PDB files, right? Or something doesn't go in the field that only stores for decimal points or whatever it is. Yeah,
that is part of the discussion that we have all the time in the center, in this development of NAMD and VMD, that a lot of the time we spend is actually on developing things that are very hard to justify and write on a grant. you know, but you need
Yes,
them. Like
yes.
those are needed, you know, like it's just that it's not very sexy when you're riding on a grant. You know, it's very hard to, but you need them. It's an important thing.
That's true. Yeah, I had this discussion recently with someone who was complaining about, like, you can only write a grant for a method, essentially, right? So I was explaining this perspective that we were just sharing, that, okay, you have to have a bigger goal, which is usually tied to something people care about. And
Yeah.
then you can sweep everything technical under the rug, essentially, right? But that's kind of the way we've been doing this.
Yeah.
We need
It's,
the things, and when we find excuses to do them.
it's an unfortunate thing, you know, like the funding mechanism, of course, is driven by this science we do, which sure, for one side makes sense, but the other side is very hard to justify the tools. Even though we are developing tools for VMD, we have a very modest type of counting 380,000 users, you know, like
Yeah.
so it still is hard to justify, you know. And,
Yeah, this is pretty striking always that last episode we had a conversation with Von Pilim, who's running Charm GUI. And he mentioned that, Charm GUI is just like a single server with 2 GPUs, despite the number of users that they have. I'm like, there's really a big mismatch in how much money we spend versus how many users something might have. VMD is another clear example, right? That in the end, it's probably mostly 3 people working almost full time, but not exactly full time on making this happen.
I mean, we are lucky to have this big NIH resource funding that supports the MD and VMD and some of these other tools that we develop. But the reason why we have them is, in my opinion, is because we always try to show the economies of scale. Like basically, like we develop these tools for hundreds of thousands of people, and it costs NIH much less than having each lab developing their own small tool. And it's much worth it. The part that bothers me about that particularly is, let's take NAMD. NAMD is, in many supercomputers in the US, the most used software, like the software that spends the most hours on running jobs, especially in supercomputers that are more targeted for large systems where people are doing like whole cells, like whole viruses and things like that at that scale. So let's take that any supercomputer like that cost anything between $100 million and like $1 billion, like in investment from like DOE, from NSF. If we can make a software run 10% faster, that computer could be 10% smaller, or maybe, like could do 10% more with it.
Yeah.
So I think a lot of the times the funding mechanisms don't think about like, okay, if 30% of the time the supercomputer, 20% of the time the supercomputer is being run in this or that software, some of the money could go to that software development to make the software run as fast as they can on that device. Like I said.
But then there's this paradox. I forget whose paradox that is, but essentially says that if you make it faster, people will use it more because now you can do 10 replicas rather than 1 replica. So
you're about the unfairness of the competition. But in terms of money well spent, I would say it's probably a question.
No, definitely. Yeah. I'm just joking here, but I also realize that the more we have, the faster the simulation engines and so on, the more we actually simulate, right? It's not that we simulate the same amount. We just find more reasons to run it 10 times and see which run is, more interesting or whatever.
I usually joke in my lab that my thesis that got even an award can be done now in a day.
yeah, that's true for most of us now. Yes. But then, so let's first get the word out, because I'm not sure. I know you did a lot of effort to make it sound in the community, but VMD 2.0 is out now and people can, install it and test it. I've been testing it for a while and it's really a major improvement in terms of comfort and usability. But there are some major developments. You are the one developing QuickMD, for example. I was just mentioning to you before we started this recording that I was very surprised as like one of the few pieces of software that I just opened up. I had a QMMM calculation to do. So I opened up QuickMD and I set up the thing in a kind of quick and dirty way, and it actually worked, which almost never happens to me. So that's an impressive feat. And I have this feeling that, VMD is full of plugins and add-ons that few people know about. So I'm thinking, like, do you have a pathway to change that?
I have the same feeling. And that's one of the main reasons why okay, since I joined Cloud Lab, I was always vocal about changing VMD. Like I had this conversation with John Stone a million times. Like we need to improve interface. And I think there was a difference in philosophy. To be honest, I think there was a big change in philosophy for both NAMD and VMD. The NAMD philosophy was always, we are serving the top 1%, like we're serving the people that are running the 100 million atom system. And the VMD philosophy was always like, we run fast and we can do crazy analysis for the large systems. And we don't care so much about most of the other users are basically like an add-on to this main development. And my philosophy is more like, we need to embrace all the users, and we need to be able to embrace users that are like not so keen on TCL. I think there's less and less people keen on TCL.
That's a big point there, yes.
Yeah. So we made this whole menu idea. So the whole menu of EMD2 was designed in CorelDRAW, like designing like workflow and like how do we click on it. And by the way, QuickMD was developed exactly the same way many years before. And the idea is like, how do we make these buttons easy? How do we make this easy for people? And we changed many times over the last year, like kind of like how we make this easier and easier and easier. And of course, there was a lot of things being developed under the hood. So kind of to your point back, we were trying to make the things that we find more useful for most people now very visible, like Covar's module, like QuickMD. Those things are now in a clear button right away. And we are trying to make them all the analysis tools in the same direction. So like instead of having like, okay, the one that always annoyed me, 3 RMSD tools. Now we have one tool that does more than the 3 together before, like, so we try to make this, instead of a hydrogen bond, we have now one that calculates contacts, hydrogen bonds, all of that in one big tool. Kind of try to group things that are somewhat similar. And so the users are going to be able to find them more easily, and they're going to discover things more easily. I think that's some of the ideas behind it. But there's always going to be hidden things. Not hidden because we want to hide them. It's just because, like, we cannot make a menu for everything. So like you're going to have to type a command to launch them. That's the...
Yeah. I'm guilty because there was Movie Maker and now there are 2 Movie Makers in VMTs. I know how these things come to life. It's like few people make their contributions and then nobody's really in charge of merging them together and maintaining them on time, right? So that's the headache of the eventual developer who takes charge.
Yeah, it's sad because you want to contribute. I think most of the users, I feel for these users that wanted to contribute and send something to us, because a lot of the times, whatever is being created already exists because it's hidden somewhere. But also, it's very hard for us to keep everything in the same standard, to keep everything working the same way, like to keep things looking the same way. That's something that we are being very careful now with VMD2, trying to have a standard. But Diego is working very hard on creating a standard, so people, when they want to develop, actually follow the standard. That's another thing that we are coming up with, like for the next few months.
That's going to be very welcome. Because, there can be a core ecosystem and a kind of additional, right?
Yeah. And we are actually...
ecosystem of tools.
There's a lot of changes also in our paradigm. Like we used to use a CVS, like controlling version system, like inside the lab. Now we're all using, like for NAMD, we're using GitLab for some time. VMD, we have migrated already like 3 or 4 times to GitLab, but never actually make the full migration. Hopefully, we are going to be done with it this month, so that people can also contribute through there. And we are moving all our manuals, all our tutorials, everything to Git, so that becomes more water. I know this does not sound very impressive for most people because people have been using these tools for a while. But one of the things that really impressed me about NAMD and VMD, like about Cloud Shooting Lab, like when I joined, is actually a lot of the tools that we are using today, like things like Git, were in place there, kind of like a version of it, something like that was already being used there. Yeah. Like there was something that looked like a Dropbox that they developed in the 1990s inside VMD.
Wow, that's impressive.
So like VMD could do things like a Dropbox. I could send you a file through VMD. Like nobody knows that. Those things were there. Like it's because they developed it when these other tools did not exist.
That's probably where the joke comes from, that, eventually every tool you make starts sending emails, right? Suddenly it becomes, I have the same problem with my libraries, that eventually they become just a kind of black hole for every idea that they ever have. So
Yeah. So it's
Someone has
very,
to be in charge.
and it's very important to clean things up. Like
Yes.
in a note for people thinking that because we are the NMD community, we fight with, let's say, the Gromax community. Like one of our main contacts and advisors sometimes, like people that we chat about stuff, like I think we exchange things. It is Eric Lindo from the Gromax community.
Mhm.
And one of the things Eric was telling me was like very strong about that. There's nobody responsible for that part of the code. That part of the code should get out.
Yes.
Like it's
Yeah, it's not very easy to get into the Gromax code base because they have very strict requirements for that. That's true.
and that's something that they had to develop over the years. It was not like
Yes.
that 20 years ago.
Yeah, I remember all the tools that were broken kind of a decade ago, maybe just because of that, just because someone contributed it and it rotted away over time.
Yeah, and a lot of the times that's why the development of these top codes is so much slower than the community wants, because like for us to keep our sanity, it
Yes.
actually is a lot of work and it's quite slow.
And as there are so many dimensions, right? Because you are also responsible for implementing a large chunk of the QMMM interface in NAMD,
Yeah,
which supports, I don't know how many codes now. I know that there are two that are kind of main. I think it's Orca and Mopac that are the main connections, right?
we developed it around Orca and Mopac. So the whole story is that we established collaboration with groups doing QM. Like, most of us, like me, pretend we know some QM, but, like we are not experts. So we collaborated with the people that like from the Orca community and the people from the Mopac community to kind of create a tool. But we also want to make sure that it was available for any software. And they were very helpful in guiding us how to make that. So the Mopac idea was like, let's make a connection to a certain paper that is as fast as possible so that a lot of people can do it. And Orca was like, okay, I want to do something with more precision, with like higher level accuracy. Orca has a lot of these tools. And that's how we made NAMD. But we also created this scriptable interface, basically. Like it's an interface that sends information in a specific format, gets information in a specific format back. And you can write a very simple Python script that can connect to absolutely any software. And we provided some exemplary scripts for Gaussian and Firefly, I think, games, TerraCam. We provided for some of them and people could build on that. Mm-hmm. We got people building all kinds of stuff, like including like Ani, like doing AI for based QM, and that's all possible through NAMD.
Yeah, I have to say that it was really very easy to set up. So I recommend to everyone who's got their like tiny KMMM project shelf for later. You can go ahead and try to set it up. It's pretty straightforward.
It is. And also another thing is that's my vision as a biophysicist, not as a chemist. Like I'm not a chemist. I cannot pretend to be one. But I think as a biophysicist, I tend to think that QMM is very important in our field. But in biophysics, you have to remember that entropy plays a large role. So like you need to have dynamics, you need to simulate for a long time. And that is why I think we developed NAMD around that philosophy, that you could also connect any of these tools to our enhanced sampling methods, to the free energy method. So you can do a strain calculation, you can do metadynamics, you can do ABF, you can use all of those things together with QMM. So you can actually get a very nice free energy profile of a chemical reaction. And I think that is a huge value compared to many of the other QM softwares and like QMM softwares.
Yes, again, that's what I did. I did like metadynamics of a proton transfer in Mopac. And it was the first time I used Colvars. It was the first time I used NAMD actually in a long time. And it all kind of came together. So again, I attest it works. And did you have to, by chance, ever use QMMM for like mechanobiology? Or is it just enzymatic reactions?
We have done it. We have a system where polarization plays a huge role. So we have this. One of the main things we studied in the lab is adhesion, like in bacteria, and those are like very important for staph infection. And the adhesins are actually the most stable mechanical proteins ever found, the mechanical bond ever found. But they also have so the adhesion part is what we call the A domain, but they also have this chain of what we call B domains. And these B domains are basically shock absorbers. They break before you break the main contact, so you never lose your grip. And they are the most stable protein folds we know under force. And they do that by having 3 calcium forming a crazy loop around just a regular IG fold. So an IG fold can break in a few piconewtons. This one goes through nanonewtons. And so these calcium loops are 3 calciums being coordinated by some amino acids. That case is where classical MD does not work so well. And we got to do with QMM. The problem is QMM was so slow that we had to go so fast to pull that things were not really working the way we wanted. Curious enough, we end up finding that we get very nice results when we do polarizable force fields. And then
that makes sense.
Yep. And then we did it with amoeba in OpenMM, and we did with Druid in MD, and the results were very similar actually. So we expected that amoeba would be better because of a better quadruple precision, but we got very nice results with Druid. And then that ended up motivating, back to your question for a few questions ago, that ended up motivating also the development of the GPU resident version of the Druid implementation in MD. So now you can do Druid GPU resident extremely fast.
Oh, wow. That's useful. Yeah. I remember probably was Frauke Grete doing bond breaking in extreme nano mechanosensation. I think that's a very rare case, right? But it's also interesting to see that you have to connect those 2 worlds where you might need to use, in the end, polarizable, right? But still beyond additive force fields for mechanosensation or mechanosensitivity.
Yeah, there's a lot that can be done with sometimes simpler tools than we want. The QMM sound like the best thing to do, but then of course the limitations. And I think that's something that I always try to tell people, that you have to use the tool that can do the job to answer the question that you want, because computational work is very expensive. We need to remember that a lot of the times the work we are doing is more expensive than the experiments because of all the raptors.
Even though we claim otherwise.
We just forget that the computer costs money.
Yes.
We always need to be careful about that. It's think about before you actually launch something. Think about what is the best way of achieving the results.
Yeah, there's I think a big question whether this whole machine learning revolution will actually result in better semi-empirical force fields. There are some that have been released recently and have big claims. I haven't still tested them, but people are thinking, okay, maybe you're going to be able to do QMM for a fraction of the cost with way better accuracy, but I think that remains to be seen. Or maybe you have some opinions.
I've seen this as there are different philosophies on how you do that, right? As far as I understand, the QM part, because there are people that are basically guessing the results with the AI, and there are people that are guessing the results of some of the calculations with AI. So you still have your QM matrices, your QM calculations the same way, but instead of calculating every integral, you guess the result of an integral. That's one approach. Mm-hmm. While the other approach is basically guess the result already directly, based on training, of course. The results that I've been seeing are pretty good. Ani, for instance, all the results I see with Ani, from Brightberg's lab at Florida, it's always very, very good. Mm-hmm. But I'm not really in the field to be reading much about it, but everything that I see is pretty impressive. I think it has a big role in the future.
More work for the QMM interfaces.
Sure, yeah. I think that as they become faster, we might also have to rework a whole interface, because the whole interface was built in the principle that the QM calculation is so slow that we don't care about the communication being slow. But if the QM calculation is as fast as the MM calculation, then the whole paradigm needs to change. You need a different way of connecting and all of that.
It's like the Born-Oppenheimer approximation of QMMM, right? If the connecting degree of freedom is way slower, then you can decouple them. Yeah, I see that. That makes a lot of sense.
I do think there is a lot of place for AI on driving the MD. I think that is something that is coming. It's already here, but it's coming our way more and more with time.
You mean defining collective variables or accelerating the simulation? Actually,
I would say accelerating the simulation, but the collective variables, sure, that there are some tools on that direction already. That's seen very nice results. I do believe that if we have enough training data, we would be able to do like microsecond long jumps, basically, like on how it's going to be in a microsecond, and force the system to go in that direction. And with that, we might be able to study processes that are from the micro to the millisecond more easily.
Yeah, like an implicit Markov state model almost.
Yeah, but not necessarily calculating the many states, but actually getting kinetics, kind of going through the process.
Yeah. Well, we can always extract it from existing trajectories, but I think the hardest part is doing this through extrapolation from what I've seen, right? So, but maybe coupling with some sort of structure prediction tools might help here.
Yeah. In mechanobiology last year, we published a paper where we were pooling on a system, and we were using our network analysis tool to calculate, basically, can we predict the force based on the network of the rupture force? And we trained, of course, in one system, we did like hundreds of simulations. And then we also tried to see how much in the past can you go and still predict. Basically, like how much in the beginning of the simulation you can be in this pooling simulation and predict what the rupture force is. And the results were pretty impressive. That we could predict the force quite well from like pretty much the beginning of the pooling.
Cool. Yeah. So there's like early something committing.
Exactly. We're talking about like, this is like the bond being committed to become like a catch bond, because it was a catch bond right on, like it was not something that happened later. So that unbinding pathway becomes committed very early.
I should apply it to some research ideas I still have in my head. Something for another conversation. Well, but overall, my impression has been that you subscribe to what I call the contact-based view of biochemistry, right? So this idea that because like there's always this idea that things have momentum or things move through space, but in reality, all this time that molecules spend waiting for something to happen is just like for the right contact to happen, and maybe a chain of contacts to form or dissolve, right? I don't know how much this kind of simple picture explains most of structural biology.
I think my main vision is very similar to that. Is just go one step beyond, maybe. That is, the idea of using networks has become one of the major things in my lab. In the network here, dynamical network analysis, what that means is you've got the contacts, exactly what you're describing, but also the correlation. So in my view, it doesn't matter if what you're seeing is a hydrogen bond, is a salt bridge, or a hydrophobic contact, whatever it is, or whatever contact that we don't need to understand well how to describe. If things stay close to each other and they move together, they are in contact, they are in a bond. And that's kind of how I treat this system. So like, I don't care what type of bond it is most of the times. I just care that this alanine is making a contact with this other, serine, and they are always together and they move together, and no matter what happens, they are together. So like, what type of contact exactly is sometimes, in my opinion, less relevant. And by having this vision, we have been able to engineer proteins, like mechanostable proteins, much better than we could with just basic biochemistry principles. Basic biochemistry would never make a mutation like we did from an alanine to a glycine and say like, oh, you're going to make the protein much stronger. And we were actually able to show, there's a paper we published a few years ago, 2.6-fold stronger mechanical fold on a system, proved experimentally, based on a single mutation like that, from an alanine to a glycine.
Nice. Yeah.
So you don't predict those things based on just basic biochemistry. This contact idea, like you're describing, the idea that they are moving together is actually
it's like partitioning a molecule into a set of interacting rigid bodies, essentially. Yeah.
And if they're interacting, like, we are happy. If they are not interacting, this is like, we can be improved. If you want to engineer that to become more stable, or you can engineer the ones that are super stable to become less stable, and that's kind of the idea behind it.
Yeah, because maybe back to the connection with visualization, there's always this problem that when you look at a new system and you don't have a mental representation of what's important, what's not. Mm-hmm. And you run a simulation and there are like things happening, but it's so hard to wrap your head around what is actually happening. But if you partition it into meaningful bits and pieces, not necessarily a domain, because a domain doesn't necessarily have to be, the single unit, but like subdomains or whatever, it
Yeah.
suddenly becomes, I mean, this is something we're just observing now doing a project here, but like it becomes so much clearer to observe what the changes actually mean and what is changing with time or with like addition of subcomponents. So I think that's a really cool kind of research project to push this vision forward as, you know, more visual and more kind of exploratory.
Yeah, we have been trying to develop tools to help us inside VMD to do things like that. Like you say, it's very hard. Also, the other thing that is very hard is to bring in statistics, like, because we do many replicas, but how do you visualize not only one network, but you did 100 replicas, so you now have 100 networks. How do you at once? Or how do you put weight on, like, okay, this is strength, but with this error bar, like, so it becomes super hard to do those things. We have been discussing how to do things like that for some time already, especially because of the number of replicas we do in the lab. Basically, any paper that comes out of my lab has at least 100 replicas. Right?
Well, yeah, that makes sense for almost like Jasinski style averaging.
Because we're doing far spectroscopy on the computer, like, so we.
Yes.
And that is something, the discussion that I had many times with Gao, and Gao started to joke that he was retiring at the right time, like, because the computers were catching up. Like the first papers on SMD from Schulten and from Grubmüller were doing like 1, 2, 3 replicates, like, and then you get these points. But now I frequently show in my talks that if I randomly pick like 3 points, you can get a completely different picture of what's happening in the system. Like you're comparing a mutant versus a wild type, because there's a distribution of these ruptures, and the distribution is quite wide. And when you get like 40, 50, 100 replicates, you actually see the distribution the same way you see in the experiments. In the experiments, they do like 1,000 pools, like, and then they see this beautiful distribution. If we do 1,000 pools, we see a beautiful distribution the same way.
Yeah, it's a great teaching point that actually, now we can also do that with simulations, right? Imagine what would someone conclude if they saw this simulation run for 1 nanosecond instead of 5 microseconds, right?
Yeah. So, and that is the thing, like, that's also a choice of how you do it. Is it better? And like, really, I'm not giving you saying one's better or the other, but like, is it better to run 10 replicates at, let's say, 100 nanosecond long, or is it better to run 100 replicates at 10 nanosecond long? Which one is better? And I think it really depends on the question you have. So when you're pulling on a system like us, when you're feeding that into like these dynamics for spectral kind of curves that you see in experiments, what we have been seeing is that many of the times it's better to go pull faster, but pull more times than pull slower and having few replicates. But again, it's the type of application we do. If you want to study like some mechanism that takes longer to move, you might be the opposite answer. So it's always important to think about the question well before you start the simulation.
Yeah, I think that was also the bottom line in like non-equilibrium alchemical for energy simulations, right? Mm-hmm. They do a lot of pullings, which are essentially the same concept of just pulling through a sort of collective variable. And they do it like hundreds of thousands of times to get the distributions.
Exactly. What I'm afraid when I see a lot of the times people coming and I talk to people that come sometimes for workshops, sometimes for that talk to us on conferences, that people are expecting a clear recipe, like I'm going to run, if I run for a microsecond, I'm going to publish my paper in Nature, like that's not like that. Like sometimes 1 nanosecond is enough, like it's just like you need to be enough for the question you're asking, like it's all about the question. Like I have colleagues here that have attosecond lasers, like, so things that happen at the attosecond scale, you do not need a microsecond of simulation, my friend.
That's true. I was recently making this figure kind of, showing what are different scales for different things that happen in simulation. I was always afraid that someone's going to take it too literally and, will come complaining to me that, oh, I run my simulation for this much. And this never happens. But then like you have to have this flexible mindset that, things can take 10 nanoseconds or 10 microseconds. And you never have a guarantee until you see.
The Nature thing that I joke, because I've seen people like from my own lab, like come in like, look, like they published this paper in this very nice journal. And there's only like 10 nanoseconds of simulation. And I'm like, was it enough to answer the question?
Yeah.
Was
That's
enough to answer the question? So done.
Fair question to ask. Exactly. If there are 2 ions in a small box of water, maybe that's all you need.
Maybe that's all you need. Exactly.
Okay, wonderful. Rafael Bernardi, thanks so much for the conversation, for the perspectives, a lot of insights into how things are developing, and the excitement about VMD 2.0 coming out soon, even stronger and better. I mean, it's already out there, but it's getting better every month, essentially.
You hope to have 2.1 by the end of the year. Let's put it that way.
Okay, that's a big promise. We'll check in after a couple of months. Yeah, thanks so much for the conversation. Hope you have a great day.
Thank you all for listening. Thank you.
Thank you for listening. See you in the next episode of Space Invaders.